looking at the side slip angle afterwards. For this one, we have both red and blue dye. So at low angle of attack, we kind of wind up with basically the same thing we had before on the conical model, and then the flow is just smoothly attached to the surface of the wing. It's a little bit more smoothly attached here just because of how the flow is injected. On the conical model, it was injected at an angle to the surface. Here it's injected pretty much exactly at the front. So we can increase our angle of attack and start to see what happens here. So unlike our conical model here, our delta wing is very specifically actually intended to generate lift, right? That said, delta wings do not function like conventional wings. Conventional wings do have vortices, but they only occur at the wingtips. Or sometimes, and I emphasize sometimes, you can see them at the edge of flaps. For example, if like a heavily laden like 737 or 747 is coming in for landing, you can sometimes see a vortex generated off of the edge of the flap where the flaps end. But you typically find them on the wings of aircraft because, again, that's when you stop having a physical barrier between the high pressure and the low pressure flow, and it's able to flow up around that surface. Delta wings, on the other hand, because the wing isn't a conventional wing, it's swept so highly back. That means the flow is able to roll over basically at every point along the wing, not just at the wing tip, which would be out here, but it's able to do it along the entire length of the wing, which is why we see a continuous vortex along the top of the wing. So a little bit of flow all the way at the front, rolls over the leading edge, and starts that spiral structure, and then more flow starts rolling over the wing further along, adding to the strength of that vortex and helping sustain it down the length of the wing. So delta wings specifically operate primarily because of these vortices. These vortices help keep the flow attached to the wing and keep it moving more rapidly than the flow underneath the wing, therefore sustaining a lower pressure on the top of the wing, higher pressure on the bottom, lower pressure on the top, and they get their lift. The problem is they tend to generate most of their lift at a very high angle of attack for a conventional wing. So, let's see here. Right now, this thing's a normal airfoil would probably be on the edge of its operating envelope already. Most airfoils have a stall angle between probably about 12 and 16 degrees. Depending on the very specific design, some of them might be able to get a little bit higher, some of them might be lower, but they will tend to be approximately in that range. This, on the other hand, is probably somewhere already between 10 and 15 degrees, so it would be normally close to a stall, but this hasn't even started generating close to its maximum amount of lift yet. So we can increase the angle of attack a little bit on this, and we start to see much more energetic vortices than we had previously, right? I mean, best case scenario, previously for the conical body, I think this is a little bit stronger than we saw, even at the very high angles of attack for the conical body. So we can see very clearly the vortices are much stronger, and we can actually see it's a little bit more clear on the right side of the body, but there's actually two vortices on each side. You have one vortex, this main vortex that runs more or less down the middle of the wing, and then there is a much smaller vortex which you'd have to get pretty close to see right now. You can kind of see blue tracing it out in fits and bursts, but there's a much smaller vortex that runs parallel to the leading edge of the wing. Red is tracing it out very clearly. Blue is only doing it occasionally. Those occasional bursts of blue dye is tracing out the vortex that runs parallel to the leading edge.
So the one that looks like it's separating from the red vortex is actually the second one?
wait, sorry, what are you talking about?
So
Down
like in
here?
regards to like how it's separating on the red side, while on the
It's
blue side
separating
it's
a
just
little bit.
yeah.
But that's I think that's mostly because actually that's where the green dye port
Oh, okay, yeah, I
injects
see,
into
yeah.
the flow.
Mhm.
You can see it on the left side. You can't see it on the right just because which side you're on. But small features like that will mess with the flow. Because I mean, effectively, you put a hole in the leading edge of the wing,
Yeah.
right? It's going to do all kinds of weird little things in that area. So I think that that's mostly why the red is getting disrupted in that vicinity.
Okay.
Is primarily because that's where the green port is. So we can keep on increasing the angle of attack on this thing. And incidentally, now you can see it for a second there pretty clearly on the blue side. Right? And again, you can see blue gets down to right about where that green port is, and then suddenly it gets sucked up by the main vortex. And then we can see the vortex burst. In this case, blue is actually bursting a little bit on the wing, but the red is bursting substantially behind the wing, right about here. It's actually it's a little bit subtle in red's case, but it's definitely bursting right there. And we're not quite seeing symmetry between the left and the right side of the body just because it's not quite perfectly leveled. It's not quite at zero side slip. It's close, but you know, this is eyeball precision going on right here. And the body itself has geometric imperfections, and there's bubbles sticking around pretty much everywhere around here. So there's tiny things that make it non-symmetric between the left and the right, and a whole bunch of those tiny things sometimes can add up to actually a pretty considerable difference, depending on exactly what's going on. But anyway, so we can see that as we increase the angle of attack, this vortex burst moves further and further up the wing. The blue started back here and is now more than halfway up the wing. The red was behind the wing and is now on it. And then at some point, increasing the angle of attack, I mean, this aircraft is pretty much entirely stalled at this point. On the blue side, it's just a diffuse cloud of dye hanging around in the wing. On the red side, it's moving, but it's still mostly stalled on us. We have a little bit more, and then we're out of angle of attack here. So just to be clear, a delta wing would pretty much never get, or never at least sustain anything anywhere close to this type of angle attack, because it's entirely stalled at this point, generating very, very, very little lift, if indeed any at all, and pretty much the maximum amount of drag it would ever generate at this point, behaving more akin to a parachute than a wing anymore. And if we bring down the angle attack, we can see that that cloud of purple dye that was hanging around on the wing starts to flow back down as the flow reattaches to the wing and is able to flow around it again. So if we look at, this thing wasn't quite zero side slip, that would explain it. So if we look at the side slip angle, we can see how that changes a little bit with how side slip changes. We're only going to look at a couple different angles, but we can see how different it'll look between the zero side slip case, which is more or less what we were looking at before, and a high side slip case, and how the vortices behave differently between the two. Just to be clear, this is definitely a very high side slip case, because that's got to be some 15 to 20 degrees off of straight ahead. So in this case, we have the angle of the body's facing, which in this case we can see from where the gear is. And then we have the direction the flow is going. And the angle between those two in the horizontal plane is our side slip angle. In the vertical plane, that would be our angle of attack, right? So we can pretty clearly see here that the right is definitely having a much harder time of it as far as forming vortices than the left side is. The left side has a vortex that just kind of keeps on going until, I mean, it might burst ever so slightly right about in this region right here, but it's still well behind the wing, whereas red is barely, from what we can see at least, it barely seems to have a vortex at all. And we can keep on increasing the angle of attack. And see, and you can actually see more or less how fast the flow is moving by how fast the pulses of dye move down the body when it's adjusted ever so slightly. So you can see that it's moving definitely faster down the left side than the right. And it's definitely moving much faster than the 2.5 inches per second that the bulk flow is supposed to be going. No, they really don't want to stick around. I was going to see if we can get a bubble to float by, and that would kind of tell us more or less how fast the flow is going right there, but they're not really cooperating at the moment. So if we keep on increasing this, same effect, we get a much more powerful vortex on the left side here. And then on the right side, for a little bit, we have a strong vortex, but it breaks up much, much, much earlier than the blue vortex. In this case, it breaks up, you know, what is that, about 25% of the way down the body. Versus if we put this back at 0 degrees side slip and give it a couple seconds to figure out what's going on. There we go. We can see that they're breaking up in pretty much the same place. Red's actually getting ahead a little bit, but again, there's some small differences kind of expected, just due to small imperfections. So the side slip angle, even a couple degrees, if we give it a second, should have a pretty pronounced effect on the flow. At this point, blue and red have pretty much just switched places on us, right? And then we can keep on going back to more or less where we were. And blue is going to be structured pretty much all the way off the wing. It's only breaking up right about when it gets to these tubes over here. And one thing to note here is you can see this even at low angles of attack, but we have some of the flow from the right side is slipping over to the left side of the body. And then even though this is already a pretty extreme side slip angle, we can increase it further still and see what will happen. And that you really can't see it because it gets behind the solid wall here, but the vortex gets all the way down right about here before it breaks up in the water tunnel. Whereas red pretty much has no vortex at all at this point. So we can see here that it doesn't just have to, from what we've already talked about a little bit with the pressure differential and the wing sweep angle, we can see that the big effect on vortex formation is more so than the pressure difference. It's how highly swept the wing is. Because if we had a wing that was perfectly perpendicular to flow, we wouldn't get any vortex pretty much at all. We would get something, but not very much. Whereas if we had the delta wing before, which was a moderate sweep angle, something like that, and it had a vortex that went more or less to the back of the wing, which is this angle of attack a little bit higher. But if we keep on bringing it back, this is almost 90 degrees of sweep, and the vortex lasts far, far longer than it did even at the highest angles of attack, or even at its optimal case in the 0 side flip condition, right? A second here. The die is not quite put on where it should be. There we go, that's a little bit better. And then we can keep on increasing the side slip angle, and the vortex more or less just continues to get more well structured. It pretty much doesn't break up at all until it gets back here where it's forced to break up by the flow, diverging into the returns. Versus zero side slip where it breaks up kind of towards the trailing edge of the wing. So at this point we've had the chance to look at the conical body, which I think I left in the sink over there. With angle of attack, and we've looked at the delta wing for angle of attack and side flip angle. Basically how the flow changes. In our case with these two bodies specifically, mostly how the vortices form, how strong they are, and how that changes with angle of attack and side flip angle, right? So, did you want to look at any particular conditions for this guy again, really quick? Anyone? Nope, not really. Okay, so again, to reiterate the previous point I made,
You hit the stop button on that control box just below the room of the table there.
the primary focus of this lab report is basically talking about what the flow is doing, what we observe the flow doing, and what the flow should be doing for these two types of bodies, and at least, and cursorily at least, why they are doing that. It is honestly quite a deep subject in why exactly they behave the way they do, so you won't get very far down the rabbit hole on those subjects. Specifically, I believe high angle of attack flow around conical and cylindrical bodies, like the conical model we have, was actually the topic of Dr. Mortos's PhD thesis. So the rabbit hole can go very, very far indeed if you follow it far enough. But that's going to be the bulk of what you talk about for the lab report, and then there'll be probably, I wouldn't expect it to be more than like a page, maybe a page and a half or so. Depends how verbose you write. On basically what our experimental setup is, what are the two models we actually looked at, and the basic parts of the water tunnel and why they are needed. It's pretty trivial in the case of the pump, but obviously we need something to move the fluid. But we also, why do we have the flow straightener, the convergence, etc., or the converging section. And then provisionally, I expect at this point this is probably going to float a couple of days based on how many groups have come through already, but it won't float more than that. In that the lab report provisionally is due 2 weeks from tomorrow, so you might get an extra day or two. I wouldn't bank on it though. Until I actually make a concrete decision one way or another on that. It's still due on Wednesday. I will, when I get a chance, post a rubric for the report, basically what I'll be looking through to grade it, and I'll also post a list of topics that you should discuss in the report to kind of give you a framework for what it should be. I think those are all the important parts. Do you guys have any questions for me right now?